Hello. In this video, we want to go back to what we started out in this section with. So the United States population is becoming more diverse. Based on the U.S. Census population projections for 2000 to 2050, the projected Hispanic population in millions can be modeled by the exponential function h of t equals 37.791 times 1.021 to the tth power, where t equals 0 corresponds to 2000 and 0 is less than or equal to t is less than or equal to 50. Estimate the instantaneous rate of change in 2010 in the Hispanic population of the U.S. Okay, so here's the thing. What we need to do is we need to figure out the instantaneous rate of change. And the instantaneous rate of change, by definition, is the limit as h goes to 0 of h, capital H, of the year and the independent value that we're working with here. And if we're working in the year 2010, that means that t is 10 in the year 2010. So it's going to be the limit as of h of, one second, let me get that right there, 10 plus h, and then minus the h of 10, and then all over h. But here's the thing. We don't actually have the ability right now to do this in an explicit format. What I mean by that, algebraically speaking, you don't have the skills to understand how to do this. What I would do instead, or what we're going to do instead, is we're going to estimate. That's a very important word when that comes up. We're going to estimate the instantaneous rate of change. Now, here's how we're going to do that. We're going to look at the limit as h approaches 0 of this entire function. But I need an expression for this up here. Notice that if I plug in 10 plus h into here and just 10 into here, now if I plug in 10 into here, that's just a number. Okay, so what we get from this is going to be the limit as h goes to 0 of, now I'm going to go ahead and plug in 10 plus h in for the t, and that's going to give me 37.791 times 1.021 to the 10th power, and then, sorry, not 10th power, 10th plus h power. Yes, that's very important. And then minus, then we have the h of 10, which is 37.791 times 1.021 to the 10th power. And then all over h. And if you look at this, notice that this h is actually the variable that we're looking at here. So what we're going to do is we're going to go to the calculator, we're going to type this in as a function, and we're going to look at what happens as h goes to 0 in both directions. Now what this means is that we need a table. So we need x, and we need, let's call it IRC. Well, let's call it just f of x. How about that? Ooh, not f. Let's go h. H and then f of h. Because this entire thing is just a function of h. Now we need numbers to the left of 0 and numbers to the right of 0. So I'm going to start out with negative 0.1. And I need to figure out what the function value is going to be. And then I'm probably going to go to negative 0.01 and then figure out that function value. And then negative 0.001. And that may be enough. It may not. It depends on where the decimals are stopping. And then once I do that, I'm going to start out with 0.1 and then do 0.01 and then 0.001 and go from there. Now, notice that I've left a little bit of space here because I don't know if I need more space here. We may not. This may be enough. Exponential functions have a way of being a little bit weird, especially when the base is really close to 1. Okay, so it's not a guarantee that that's enough data. But what we're going to do is we're going to go ahead and go to the calculator and see if it works. I'll see you there. Okay, welcome to the calculator. Let's go into y equals, and then let's type in our function. Alpha y equals enter. And what we have is 37.791 0.791, and then times, parentheses, 1.021, close parentheses, caret, so to the power of 10 plus h, but we don't really have an h in here, so let's make that just 10 plus x. Then right arrow. And then notice now that we need to do a minus, and then 37.791. And then parentheses, 1.021, close parentheses, to the 10th power. And in the denominator, put an x. All right. Now, if you want to, we can actually go ahead and graph this. Well, if I go to the standard window. And we can kind of see that it's going to be having a limit that will approach something there. So that's good. So let's go to vars, right one, enter, enter, and then tell it to do it of negative 0.1, enter. I see 0.96581333496. I'm writing down all of these for a reason. Then do second enter, make that negative 0.01. So it gives me 0.966 71 68 423. This time we're going to do negative 0.001. So it gives me 0.966807255. Okay, good. Now notice what's happening here is that every time I add in a 0, there's another decimal that is the same as the one previously. And that's going to keep happening. Now, what I'm expecting is that if I go one more time, so if I do negative 0.0001, excellent. Yes, that's staying an 8. Now, I expect the next one, this will stay a 1, and then so on and so forth. But the reason that this is important is because we want to round it to 3 decimal places. So I needed to be sure that this decimal here needed to be an 8. So this is going to make sure that we go to negative 0.0001, which is 0.9668163. Good. But notice that this is converging to a number. It's approximately 0.967. Notice if we do one more with 4 zeros and a 1. So it's 0.96681, and then probably a 7 on the next one. Do this again. So 5 zeros and a 1, which of course would be what? Tenths, hundreds, thousands, 10,000s, 1 millionth. So negative 1 millionth. So 0.96681 is what that one is. And this may be the last that we see of this. If I throw in another 0.1 there, ooh, we may start getting to some really weird numbers at this point. 0.1. Ooh. 0.1. Ah, interesting. Notice that we really needed to just keep going. Actually, I'm not sure that that's the case. I think at this point, we're starting to get rounding errors. Yeah, we're getting rounding errors here. Yeah, then it's a 0. So basically, what's happening at this point, once you start seeing that weirdness starting to happen, we're starting to see that the calculator has rounding errors in the sense that it's an underflow or an overflow error somewhere in there. And what's happening is it's really messing up what's happening in the background in the calculator, because there is a memory limit to what it can do. So once we start working with really small numbers or really large numbers, one of the two, the calculator starts doing weird things. So if we go back up here, notice that I believe this. I do not believe this one, because notice that it's actually cutting off some of the. In fact, I just believe this one. it's starting to cut off decimals here. So weird things are starting to happen. This one I absolutely believe, though. So rounding it after 3 decimals is where that's probably a good idea. Now let's go in the reverse direction. Vars, right 1, enter, enter. Where did I put that? Okay. Vars, right 1, enter, enter. Parentheses. Now positive 0.1. And notice that it is not the same thing as negative 0.1. It is 0.96782264421. Vars, right 1, enter, enter. Make it 0.01. So it gives me 0.96691777714. Okay, good deal. Do this again. Make that 0.001. Make it 0.966827345. And let's go one more just to verify that the next number should be an 8. So it gives me 0.0001 was 0.9668183. In fact, that one may even be wrong, but I wanted to verify that that was in fact an 8 right there. That's good. Alrighty. Well, that's actually a really good thing. So if we go back to the table, or the graph here, let's go ahead and zoom in. Yeah, you can kind of see it doing its thing there. Now, if you were to just look at this, you might think, oh, that's going to 1. So you would actually be wrong here. So just be very careful that that you're not just looking at the graph and saying, oh, it just kind of looks like that's happening, and go from there. Alrighty, now that we know this, we're going to go back to the notes and we're going to finish up this question. I'll see you there. Hello. Welcome back to the notes. Okay, so all I've done is I have included what we saw on the calculator here. Now notice that, again, we started kind of losing decimals, and that's fine because we're actually going to round this anyway. Notice that I'm going to go ahead and round it after 3 decimal places, and that's perfectly fine to do because all of these are kind of looking like the same, like they're the same thing. So it's going to be 0.966 from the left-hand, sorry, 0.967 from the left-hand side, and about 0.967 from the right-hand side. And so that tells me that this is going to be 0.967. And now, of course, again, in this particular question, the units were million people per year. Now, what this tells me is that in the exact year of 2010, the Hispanic population will be increasing, if this model is correct, by 0.967 million people per year. In other words, 967,000 people per year. Again, this is all just an estimation. We don't know if it's correct or not yet, but we're going to start looking more at the census, or well, we're going to get the census data more after this year, and it'd be interesting to see if the actual projection was correct or not. It's always dangerous to rely upon estimates or projections because those aren't relying on intermediate data or data to the left and right of it to figure stuff out. It's taking stuff that we've seen and then projecting it into the future. And that's a problem because, well, frankly, we never know what's going to happen in the future. But it is always interesting. Alrighty. Well, I believe that's it for this video. I'm going to go ahead and end it here, and I will see you in the next one. Have fun.